We now know that the expected value is just another way to compute a mean, specifically when each value in the data set may or may not be weighted the same. So here's our formal definition. The expected value of a random variable, capital X, is the expected long-run average of that variable. So we write it like this. We say the expected value, or E of capital X, equals, another way to write this is as the Greek letter mu. So you could either write E of X or mu, and this is the Greek letter M called mu, and it is the sum, or the addition of all of the probabilities of the values times the associated value. P of X can also be thought of as the weight of the value capital X equals little x. If each of the values has equal weight, then this formula reduces down to the regular mean computation we are used to. So first of all, you see a capital X and you see a lowercase x. That is initially kind of confusing because, well, are we dealing with lowercase or capital? Well, capital X is just the symbol representing the variable, and little x is one of the possible values that capital X can take on. Okay, so that's what we mean. We mean that the random variable takes on this value instance. Okay, so little x is just one of potentially many possible values of capital X. So in statistics and probability, we usually use capital letters to denote a random variable, not always, but a lot of times. And then the lowercase x represents a particular value that can take on. Okay, so focusing a little bit on this formula and how it reduces down to the regular mean computation we are used to. Let's suppose that we have maybe three values with equal weight. Well, what would that mean? Well, that would mean that the expected value of this random variable would be, according to this formula, it would be the probability of that value. Well, if it has an equal weight as all the others, and there are three values, then it would be 1/3 of that first x, that first value. I'll denote that x1, plus, according to the formula, the next probability, which is 1/3, again, equal weight as x1, but this is for x2, and then plus 1/3 times x3. Now, if you notice that since these are all the same, this is the same thing as writing x1 over 3 plus x2 over 3 plus x3 over 3. And since the denominators are the same, I can just add the numerators and notice that this is exactly the same thing as our old average formula. So this is a more robust form of an average because it allows for the possibility where these aren't all 1/3. In fact, maybe x1 occurs 2/3 of the time, and x2 and x3 both occur 1/6 of the time. Well, that still adds up to 6/6, which would still account for 100% of the time, but it would be putting more weight or more value on x1. Okay, so a random variable is a variable. We use this phrase random variable. So what does that mean? Well, in computing averages, we don't ever think about our values of x as being random. If you get 3 test scores and they're 70, 80, and 90, then you got 3 test scores and they are 70, 80, and 90. There's no uncertainty associated with that. But oftentimes when we compute expected values, we want to predict the average outcome. We want to calculate an average outcome based upon things that haven't happened yet. And as long as we know the likelihood of those things happening, we can still calculate an average value. So a random variable is any variable whose outcome takes on certain values with a specified probability. Okay, so the only difference between a variable and a random variable is a random variable takes on values according to the toss of some n-sided coin. So maybe if there are two possible values, maybe one occurs 50% of the time and the other occurs 50% of the time, or maybe one value occurs 30% of the time while another occurs 70% of the time. The idea is that their possible outcomes are known, but we're not sure which of those values will come up. We only know what the likelihood of each value is. The probability distribution is just a description of that random variable, for that random variable, of the values and their associated probability. So usually we list this as a table, or we call a probability histogram, which is kind of like, without getting into the technicalities, like a bar chart. But I'll demonstrate an example here to show you exactly what we mean by this. Let's take a look at an example. Suppose we toss a fair two-sided coin. Fair two-sided, fair means that equally likely chances. If the coin comes up heads, you pay me $2. If the coin comes up tails, I pay you $4. This might look familiar. Give the probability distribution as a table and as a probability histogram for x equals the amount in dollars you win or lose. Okay, so there's our random variable. We want to study the amount that we win or lose. Then determine and interpret the expected value of x. Okay, so x again is the random variable. It has two possible values. So I'll write this column. Usually you'll see it appear like this: x equals little x. Okay, well, what are those little x's that capital X can take on? So first of all, I'm going to write it as a set, and x, the amount you win or lose, could either be $2 or $4. The difference here is, if you pay me $2, from your perspective, you have lost $2. So it comes up as a -2, or you win $4. So how much you win or lose would be +4. I'll omit that positive sign there, but I want to emphasize that is a positive because you're receiving that. So the values, the little x's that this variable can take on, are -2 and +4. And now I want to know what's the probability of each of these values. Well, since this is a fair two-sided coin, the probability is going to be 1/2 or 50%, and 1/2 or 50%. So you can see that this is just a table that describes the outcomes and their probabilities. And I should point out that if you sum these, you need to get 1. Right? Because something's got to happen 100% of the time. And if they don't add up to 1, that means we've missed something. There's another event that we haven't taken into account. So if we said 20% of the time you pay me $2 and 60% of the time I pay you $4, then what happens the other 20% of the time? We need to know that in order for this expected value to make sense. Okay, another way, so this is as a table. We could do this as a probability histogram. And the histogram, what it's going to have is it's going to have the values of capital X over here, and it's going to have the probability of each value over here. Okay, and so without getting too technical about this, since there are only two values here, we're going to say, well, it could be -2 or +4. And we know that in this case, 50% is the probability of each. So we're going to have one bar here that just shows that that event has a probability of 50%. And then we'll draw another bar here that says that event has a probability of 50%. So there's our probability histogram. Okay. One's a little bit more visual than the other. One will, especially when there are a lot of events, it's hard to look at a table and kind of see likelihoods. The histogram does a much better job of organizing that for us. Okay, so determine and interpret the expected value of x. So I want to know, on average, right? I want to know the expected value. So on average, how much am I going to win or lose? What do we mean on average? Well, we toss a fair-sided coin, so we want to know, on average, how much do we win or lose for each toss? So the expected value of x, which again, we could write that, or we could write mu equals, and that's going to be the sum of the probabilities times their values, or the values times their probability. So half of the time you're going to lose $2, plus half of the time you're going to gain $4. And that comes out to -1 plus 2. So you're going to gain $1 on average per one toss. Okay. As before, if we were to play this game twice, we could also think about this as you're either going to lose 2 or gain 4. So if we played twice, you would expect to lose $2 once and expect to win $4 once. We'd expect one head and one tail. And so divided by 2 tosses, this is in dollars, notice that we still get $1 per toss. This formula can be helpful and detrimental at the same time. Helpful because it gives us a really quick computation, but detrimental in that we might forget that this is still just an average. And so we need to know, okay, what are the units of X? Well, it's in dollars, and then per what? Well, in this case, we're tossing a coin once, so it's going to be per toss. So you expect to win $1 per toss if you play over and over again. Okay, what does that mean? Well, in mathematical terms, that means if you played infinitely many times, you would win exactly $1 per toss if you distributed your losses and gains. Keep in mind that there's only 2 outcomes. It's either lose 2 or gain 4. So the $1 per toss says if you took all of the times that you won $4 and all the times that you lost $2, added all those amounts up, and then divided by the number of times you played, it should come out to $1 per toss. Now, is it possible that you play twice and you lose $2 both times? Of course. This is just the expectation of that outcome. Example 2, let's change this a little bit. Suppose we toss a biased two-sided coin where heads shows up 90% of the time. If the coin comes up heads, you pay me $2. If the coin comes up tails, I pay you $4. Of course, it's not going to be a good game because most of the time you're paying me $2 and very infrequently I'm paying you $4. Give the probability distribution as a table and a histogram for X equals the amount you win or lose. So, okay, once again, the values that this random variable can take on, and sometimes instead of saying X equals X, we'll just say little x. These are the possible values. Once again, we know that it's either -2 or +4. The only thing that has changed is the probability. Okay, well, what is the probability of losing $2? It's 90%, because 90% of the time, heads comes up. Well, then how often are you going to win $4? Well, remember, these have to add up to 1, and so if you lose 90% of the time, you're only going to win 10% of the time. And to get the probability histogram, this is going to look different now. For capital X as -2 and +4, we know that, I'm going to do increments of 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. You're going to lose $2 90% of the time. And you're going to win $4 10% of the time. So this histogram gives us a nice visual because, if you think about it, it's a stark contrast between winning $4 and losing $2. The expected value of X, which once again is how much we're going to win or lose in dollars per time that we play, which is per toss. So the expected value of X is going to equal the value times its probability plus the value probability times its value. And let's see, this will be -$1.40 per one toss. So since it's negative, remember this is from your perspective, you're going to lose $1.40 per toss on average. Now another way you could think about this is, since this is a 90-10 split, you could think if you played 10 tosses, you would expect to get 9 heads and 1 tail. and every time you get heads comes up, you lose $2, so that's going to be a loss of $18. A loss of $18. And one time you win, so you're going to get $4. And okay, well that's a total of a loss of $14 across 10 tosses. Well, notice once again that comes out to minus $1.40 per one toss. So we're still computing an average here. It's just a much nicer, cleaner version. You can think about 9/10 weight on -2 and 1/10 weight on 4. Let's shake this up a little bit and change the random variable itself. Suppose we toss a fair two-sided coin a total of 3 times. 3 times. Give the probability distribution as a table and as a probability histogram for x equals the number of heads that are tossed. Then determine and interpret the expected value of x. Okay, so what are we counting here? We are counting the number of heads that are tossed in 3 coin tosses. So if I toss a coin 3 times, I may not get any heads at all. I may not get any heads at all. That's not going to have a high likelihood probably, but it can happen. I could maybe just get 1 head and 2 tails. I could get 2 heads and 1 tail, or I could actually get 3 heads and no tails. So I actually have 4 possible outcomes here for the number of heads that I toss. Okay, so what are the possible values? They're 0, 1, 2, and 3. Now we're not given the probabilities. All we know that every toss is going to result in a fair outcome. Okay. Well, what I need to do is figure out what's the probability of getting 0 heads, 1 head, 2 heads, and 3 heads. Well, if you think about it, there are 2 outcomes for each toss, heads or tails, and that's just for toss 1. Now I could model toss 2. I could just build a tree diagram for this. Toss 2 could be either heads or tails, depending on what I got first. There's toss 2. For toss 3, I could get heads or tails, heads or tails, heads or tails, and heads or tails. So I know that each one of these is equally likely since this is a fair coin, and so each of these would be 1/8 probability. We'll actually do this without doing a tree diagram, but I just want to motivate the computation and just remind us how we could actually use combinations. How we could actually use combinations to solve this. So notice that this adds up to 100% of the time, right? Each of these is going to be equally likely. There are 8 possibilities. 2 times 2 times 2. There are 2 outcomes, each of which has 2 outcomes for toss 2, each of which has 2 outcomes for toss 3. That's a multiplication problem. Okay, well I could actually look at this table and now figure out the number of ways that there are to get 0 heads. Okay, so to get 0 heads means I would get all tails. That would be just this one outcome here, which has a probability of 1/8. Okay, now the other way of thinking about this, and the way I really want you to think about this, is I have 3 tosses. 3 tosses. Toss 1, toss 2, and toss 3. And I want to count the number of ways that in these 3 slots I could pick 0 of them. Yes, I said take 3 slots, choose 0 of them, and put a head in those 0 slots. Fill the remaining slots with tails. Well, there is only one way you could do that, right? You could, if I count the number of ways that I could put 0 heads in here, well, there's only one way I could do that. That's by not putting any heads in there, divided by the total number of possible outcomes, which I know is 2 times 2 times 2 equals 8. All right, so we drew the tree. We could count the 8 outcomes, but I know there are 8 possible outcomes here. And how do I count the number of ways, or this numerator? How do I get that numerator? Well, to get that numerator, I just asked from 3 slots, choose 0 of them. Remember, this is the same thing as writing number of combinations of taking 3 slots and picking 0 of them. And there's one way to do that. That's by not picking any at all, and then filling the rest of them with tails. Might make more sense when we move to 1 now. So how many ways are there to get exactly 1 head? Well, let's look at the table over here. To get just 1 head would mean, well, if I get heads on the first, I can't get heads on the second or the third. So that's going to be this one here, heads, tails, tails. Then I could get tails, heads, tails. Or I could get tails, tails, heads. So I need 2 tails and 1 head in there. So that's 1/8 plus 1/8 plus 1/8. Well, that's 3/8. Okay, as far as counting, I can actually compute this 3 the same way. I know there are 8 outcomes, 2 by 2 by 2. And what I'm going to be asking for is how many ways are there for me to pick one of these slots to put a head in. Well, I could maybe put the head there. And then there's only one way I could fit the rest of them with tails. That's by just putting a T and a T in toss 1 and toss 3. So what I'm asking for is how many different ways can I pick 1 slot from 3 to fill with a head? 3 combination 1 is equal to 3. I could do a similar process for this next one. I could say, well, I know there are 8 outcomes. How many ways are there for me to get 2 heads? Well, that's the question of how many ways can I pick 2 slots and place my heads down? Well, I could pick these first 2 slots and then put a tail here. The idea here is that from 3 slots, choose 2 of them, put your head in there, and then there's only one way to fill the rest with tails. 3 combination 2 comes out to 3, and then divided by 8. Now, again, I could come over here and count that. I could say, well, heads, heads, tails. There's 1. Heads, tails, heads. There's a second one, and then tails, heads, heads. There's my third one. All right, last but not least, how many different ways are there for me to get 3 heads? Well, there's only one possibility left over here, so that should be kind of apparent to us. There's only one way, 1/8 of all the possibilities are all 3 heads. And again, I could do this in a similar way. There are 8 possible outcomes. How many different ways are there for me to have 3 slots and pick 3 of them into which I'm going to put heads? Well, there's one way you can do that, and that comes out to 1/8. Great, now we have it. So let's draw our, we have our probability table. Let's actually draw our histogram. And so in this case, I could actually connect the bars because there's nothing in between. And I have up to 3/8. So I'll just say that this is 3/8 right here. And so the probability that I get 0 heads is a 1/8 chance. Probability that I get a 1 is a 3/8 chance. Probability of getting 2 heads is a 3/8 chance, and probability of getting 3 heads is a 1/8 chance. So I can actually make it look like this. And so we see that we're going to expect to get 1 or 2 heads the majority of the time, and very infrequently, as we might expect, would we get no heads or all heads. It's possible, it does occur every 8 times you repeat a 3 tosses. Every trial, you'd expect 1/8 of all those 3 coin tosses. You would expect to get 0 heads or all 3 heads. Now, to get the expected value, okay, and then these are the values of x. This is the probability of each of those values. Finally, what's the expected value? Well, the expected value of x is going to be the number of heads per 3 coin tosses, or per 3 tosses of the same coin. Doesn't matter how you want to phrase that. It's the number of heads expected every time we toss a coin 3 times. So from our probability distribution table, we know that 1/8 of the time we'll get 0 heads, 3/8 of the time we'll get 1 head, 3/8 of the time we'll get 2 heads, and 1/8 of the time we'll get 1 head. Oh, and we forgot to just establish these do add up to 1. Okay, so I get 3/8, I get 6/8, that's 9/8, and then I get 10/8 here, which is going to come out to 1.25. Okay, now this is again the number of heads, and this is for every time we toss the coin 3 times. Wow, that's a strange value. How can you have 1 1/4 heads on average across 3 tosses? Well, it's impossible to get 1/4 of a head. We're just saying that if you looked at, you tossed a coin 3 times, and then you tossed the coin 3 times again, and then you tossed it 3 times again, and each time you recorded the number of heads, and then you divided by the number of times that you tossed the coin 3 times, then you would, on average, have just a little bit more than 1 head per toss on average. So if this would help us, perhaps, if we were playing a game where I would only win money if I tossed 2 or more heads in those 3 coin tosses, then I may not want to play this, because I'm expected to actually get fewer than 2 heads on average. As a result, we have an expected value calculation, and this is for a random variable that doesn't represent wins or losses, but it actually counts the number of heads that we toss.